There is a lost planet wandering through dark space, invisible to our eyes, but as real as the Earth beneath your feet. This mysterious world is somewhere on the edges of our solar system, silent and hidden, but with enough power to destroy everything we know. Scientists have discovered strange clues, as if something giant were pulling other planets in a bizarre way, distorting their orbits like an invisible predator manipulating its prey. This ghost planet could be 10 times larger than Earth, a colossal mass floating in the frozen void, waiting for the right moment to reveal itself. But here is what keeps astronomers awake at night. If this world really exists and decides to come closer, its massive gravity could throw giant asteroids in our direction, push Neptune and Uranus out of position, and transform our organized solar system into a cosmic battlefield of collisions and chaos. How is it possible that an entire planet is hiding in our own cosmic backyard, watching everything like a silent eye in the darkness of space, and we still cannot find it? Subscribe to the channel, leave your like and comment from which part of the world you are watching, get comfortable and relax. Let's begin. There is something out there in the dark, something massive and silent, drifting through the frozen outer reaches of our solar system, where sunlight arrives as little more than a dim memory of warmth. We cannot see it. We have never photographed it. No telescope has captured its image against the star-filled backdrop of deep space. And yet, despite this absence of direct evidence, despite the fact that it remains hidden from our most sophisticated instruments, many scientists believe it is real. They believe that somewhere beyond Neptune, beyond Pluto, beyond even the scattered belt of icy debris that marks the edge of what we once thought was the boundary of our cosmic neighborhood, there orbits a world, a planet perhaps 10 times more massive than Earth, dark and cold, taking thousands upon thousands of years to complete a single journey around our sun. They call it Planet 9, though some prefer the older, more evocative name, Planet X. The unknown world, the hidden giant. And if it exists, if it truly lurks out there in that vast darkness, its presence alone could reshape everything we thought we understood about the stability and structure of our solar system. This is not the stuff of science fiction, though it certainly sounds like it. This is not ancient astronaut theory or fringe speculation whispered in the corners of the internet. This is serious science, published in peer-reviewed journals, debated at conferences, and investigated by some of the most respected astronomers in the world. The idea emerged not from imagination, but from observation, from the careful study of smaller, distant objects whose orbits seemed wrong, tilted and stretched in ways that defied explanation unless something large and unseen was pulling on them from the darkness. These objects, frozen worlds smaller than our moon, tumbling through the outer solar system, were not where they should be. Their paths were distorted, clustered in patterns that seemed too deliberate to be random chance. It was as if an invisible hand had reached out from the void and nudged them into alignment, the gravitational signature of something enormous hiding just beyond the reach of our instruments. Before we go any further, before we venture out into that cold and lightless frontier where this ghost planet might dwell, I would like to know where you are right now. What part of the world are you listening from? What time is it where you are? Are you settling in for the night, letting these words carry you towards sleep? Or are you in some quiet moment of the day, seeking a different kind of journey? It is strange to think about, is it not? Here we are, separated by distance and circumstance, yet connected by curiosity, by the shared wonder of looking up at the night sky and asking what else might be out there, waiting to be found. If you enjoy these kinds of explorations, these slow and careful considerations of the mysteries that still surround us, I would be grateful if you would subscribe to this channel or leave a like. It is a small gesture, but it helps this content reach others who might also be searching for something to wonder about in the quiet hours. But there is no pressure, no urgency. You are here now, and that is enough. So settle in, make yourself comfortable, let the concerns of the day fade into the background. We are going to take our time with this story because it deserves patience. We are going to follow the clues that led astronomers to suspect this hidden world exists. We are going to explore what it might be, where it came from, and what its presence might mean for the future of everything that orbits our sun, including us. We are going to ask whether the solar system we thought we knew is truly as stable and predictable as we imagined, or whether we have been living in a kind of cosmic ignorance, unaware of a massive neighbor whose gravitational influence touches everything, including the trajectory of objects that could one day cross paths with Earth. The story of Planet 9 begins with absence, with the things we do not see rather than the things we do. For most of human history, we believed the solar system was a small, tidy place, the sun at the center, a handful of planets arranged in orderly orbits, and beyond them, nothing but empty space stretching toward the stars. Even after we discovered Uranus in the late 18th century and Neptune in the mid-19th, the basic picture remained simple. The solar system had boundaries, it had edges. We knew what was out there because we had catalogued it, measured it, mapped it, but that confidence, that sense of completeness was always premature. Every time we developed better instruments and looked more carefully, we found more. The asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, dwarf planets like Pluto and Eris, and beyond even those, the scattered disk, a region of space where icy bodies drift on elongated, eccentric orbits that take them far from the sun before swinging back again. It was in this scattered disk, this realm of distant and lonely objects, that astronomers began to notice something odd. The orbits of these trans-Neptunian objects, as they are called, did not behave the way theory predicted. When you have a collection of small bodies orbiting a star with no large planets nearby to disturb them, you would expect their orbits to be randomly oriented, scattered in all directions like leaves blown by the wind. But that is not what astronomers found. Instead, many of these distant objects had orbits that were aligned, clustered together as if something had organized them. Their orbits were tilted at similar angles. They swung out into space in similar directions, and their closest approaches to the sun, their perihelia, were grouped in a way that seemed too precise, too coordinated to be mere coincidence. At first, this clustering was easy to dismiss. Perhaps it was an observational bias. Perhaps astronomers were simply finding more objects in certain regions because those were the areas they were looking at most often. But as more objects were discovered and the pattern persisted, that explanation became harder to accept. The clustering was real. Something was shaping these orbits, bending them, guiding them into alignment. And the most straightforward explanation, the one that required the fewest leaps of logic, was that a large, unseen planet was out there exerting its gravitational influence on these smaller bodies. Its mass was pulling them, subtly but persistently, into the patterns we were observing. In 2015, two astronomers, Konstantin Batygin and Michael Brown, published a paper that brought this idea into the scientific mainstream. They used computer simulations to model the orbits of the trans-Neptunian objects and asked what kind of unseen object could produce the clustering that was being observed. Their answer was striking. The best fit, the model that most closely matched reality, involved a planet. Not a small one, not a dwarf planet like Pluto, but a true planet, a super-Earth with a mass 5 to 10 times that of our own world. This planet, they suggested, orbited far beyond Neptune, so far that it took between 10,000 and 20,000 years to complete a single orbit around the Sun. Its orbit was highly elliptical, stretched out in a long, narrow path that brought it no closer than 200 times the distance from Earth to the Sun, and carried it as far as 1,200 times that distance at its farthest point. To put those numbers in perspective, consider this. Neptune, the most distant of the 8 recognized planets in our solar system, orbits at an average distance of about 30 times the Earth-Sun distance. Planet 9, if it exists, would spend most of its time more than 20 times farther away than Neptune. At that distance, the Sun would no longer appear as a brilliant disk in the sky, but as a bright star, still the brightest object by far, but reduced to a point of light. The cold at that distance is almost unimaginable. Temperatures would hover just a few dozen degrees above absolute zero. Any atmosphere the planet might have would be frozen solid, collapsed onto its surface like snow. If there is a landscape there, it would be one of eternal twilight, a world of ice and rock where nothing moves, nothing changes, and the only sound, if sound could travel in that near vacuum, would be the faint whisper of cosmic radiation passing through the void. But we are getting ahead of ourselves. Right now, Planet 9 is still a hypothesis. It has not been found, no one has seen it directly, no photograph exists, and that is important to understand from the beginning. This is not a story about a planet we know is there. It is a story about a planet that might be there, a world whose existence is inferred from its effects rather than observed directly. It is a ghost story, in a way, a tale told not by the ghost itself, but by the things it disturbs. And like all good ghost stories, it raises more questions than it answers. If Planet 9 is real, where did it come from? How did it end up in such a distant, eccentric orbit? And most importantly, what does its presence mean for the rest of the solar system, including the small, rocky planet we call home? The universe is vast, far larger than our minds can truly comprehend. Even our own solar system, which is just a tiny speck within our galaxy, contains distances so enormous that light itself, traveling at 300,000 kilometers per second, takes hours to cross from one side to the other. We live in a neighborhood we thought we understood, a small collection of worlds orbiting a familiar star. But now, at the edge of that neighborhood, there might be something we missed, something huge, something powerful, something that has been out there all along, shaping the paths of other objects, influencing the architecture of the solar system in ways we are only beginning to understand. And if we are only now noticing it, only now piecing together the clues that hint at its existence, what else might we have missed? What other hidden giants might be drifting through the dark, too far and too faint for us to see? These are the questions that keep astronomers awake at night. These are the mysteries that drive them to spend years scanning the sky, searching for the faintest glimmer of reflected sunlight that might reveal the location of this hidden world. Because finding Planet 9, if it exists, would not just be a triumph of observational astronomy. It would be a reminder that even in our own cosmic backyard, even in a space we have studied for centuries, there are still profound unknowns. It would be a humbling realization that the universe does not give up its secrets easily, that some things remain hidden until we are clever enough, patient enough, and persistent enough to find them. And so we begin this journey with uncertainty, with the possibility rather than the certainty of a hidden world. We begin with the recognition that science is not about absolute knowledge, but about the careful accumulation of evidence, the testing of hypotheses, and the willingness to revise our understanding when new information emerges. We begin, as all good explorations do, with a question rather than an answer. Is there a ninth planet lurking in the outer darkness of our solar system? And if there is, what might it mean for us? The night sky above you, wherever you are, is filled with light from distant stars, some of them so far away that the light you see tonight began its journey toward Earth before human civilization existed. But somewhere in that sky, in a direction we have not yet pinpointed, there might be a world much closer, a planet that belongs to our own sun, our own system, and yet remains as mysterious as anything beyond. It is out there, perhaps, moving slowly through the frozen dark, completing its vast orbit in silence and solitude, unaware that on a tiny blue world, much closer to the sun, curious minds are searching for it, trying to bring it out of the shadows and into the light of knowledge. To understand why astronomers believe Planet 9 might exist, we need to look carefully at the clues, the breadcrumbs of evidence scattered across the outer solar system that seem to point towards something hidden. These clues are not dramatic. They do not announce themselves with fanfare. They are subtle, mathematical, written in the language of orbital mechanics and gravitational dynamics. But to those who know how to read them, they tell a compelling story, a narrative of invisible influence and distant presence. They suggest that the solar system we thought we knew is incomplete, that our maps of the cosmic neighborhood have a significant blank spot, and that something massive is out there, quietly pulling on the fabric of space and time. The first and most important clue comes from the orbits of distant trans-Neptunian objects, those small, icy worlds that drift through the outer reaches of the solar system far beyond the orbit of Neptune. These objects are difficult to study. They are small, often no more than a few hundred kilometers across, and they reflect very little sunlight. Finding them requires patience and powerful telescopes, and even then, each discovery is a triumph of careful observation. But over the past few decades, astronomers have found enough of them to begin noticing patterns, and it is in those patterns that the mystery deepens. If the outer solar system were governed only by the gravity of the Sun and the 8 known planets, we would expect the orbits of these distant objects to be more or less randomly distributed. Some would orbit closer to the plane of the solar system, the imaginary disk that contains most of the planets. Others would be tilted at various angles. Their orbits would point in all directions, a chaotic jumble reflecting the random collisions and perturbations that shaped them billions of years ago. But that is not what we see. Instead, a significant number of these objects have orbits that are aligned in a very specific way. Their perihelia, the points in their orbits where they come closest to the Sun, all seem to point in roughly the same direction, and their orbits are tilted at similar angles relative to the plane of the solar system. This clustering is statistically unlikely to be random. The odds of it happening by chance, according to calculations done by Batygin and Brown and later confirmed by other researchers, are somewhere in the neighbourhood of 1 in several thousand. Imagine you are standing in a vast empty field and you throw a handful of stones into the air. When they land, you would expect them to scatter in all directions, some near, some far, but with no particular pattern. Now imagine that instead all the stones land in a narrow arc, all pointing roughly the same way, all at similar distances from you. You would immediately suspect that something other than random chance was at work. Perhaps there was a wind you did not notice, or perhaps the ground sloped in a way that caused the stones to roll. Something external shaped their final positions. This is the logic that underlies the Planet 9 hypothesis. The clustering of orbits is the effect, the hidden planet is the cause. But the clustering is not the only clue. There is also the matter of high-inclination objects, trans-Neptunian bodies whose orbits are tilted at extreme angles relative to the plane of the solar system. Most objects in the solar system orbit more or less in the same flat disk, a relic of the rotating cloud of gas and dust from which the Sun and planets formed. But some of these distant objects have orbits that are tilted far out of that plane, some by 30 degrees, some by even more. A few are nearly perpendicular to the solar system's disk, looping high above and below the orbits of the planets, like riders on a cosmic roller coaster. These extreme orbits are difficult to explain with conventional models. There is no obvious mechanism within the known solar system that could tilt objects so dramatically. But if Planet 9 exists, its gravity could do exactly that. Over millions of years, repeated gravitational interactions with a massive, distant planet could slowly twist the orbits of smaller objects, pulling them out of the solar system's plane and into these high-inclination paths. Then there is the curious case of detached objects, trans-Neptunian bodies whose orbits are so large and so elongated that they never come close enough to Neptune to be influenced by its gravity. These objects are truly isolated, drifting through space on paths that seem to have been set long ago and never disturbed since. Their existence raises a question. If they are too far from Neptune to be affected by it, what put them on these strange distant orbits in the first place? One possibility is that they were scattered outward by a larger planet early in the solar system's history, nudged into their current paths by gravitational interactions with something massive. If Planet 9 exists, and if it formed closer to the Sun before being pushed outward by the gravity of Jupiter or Saturn, it could have scattered these smaller objects into their current orbits as it migrated to its present location. There is also the issue of orbital resonances, a phenomenon where the orbital periods of two objects are related by a simple ratio. For example, Neptune and Pluto are in a 3:2 resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. This relationship is stable and keeps the two objects from colliding even though their orbits cross. Some trans-Neptunian objects appear to be in resonance with something unseen, something with an orbital period that matches the predictions for Planet 9. If that resonance is real, it would be powerful evidence that the planet exists, because resonances do not happen by accident. They are the product of long-term gravitational interactions between massive objects. Each of these clues on its own might not be enough to convince skeptics. Clustering could be a statistical fluke. High-inclination orbits could have other explanations. Detached objects could have been scattered by Neptune in the distant past when its orbit was different. But taken together, the clues form a coherent picture. They point toward a single, unified explanation. There is something out there, something large and massive, something that has been quietly shaping the outer solar system for billions of years. And the more data we gather, the more objects we discover, the more difficult it becomes to explain all of these features without invoking Planet 9. Of course, absence of evidence is not evidence of absence, and the scientific community is rightly cautious. Many astronomers remain skeptical, not because the hypothesis is unreasonable, but because extraordinary claims require extraordinary evidence. A new planet in the solar system would be a major discovery, one that would rewrite textbooks and change our understanding of how planetary systems form and evolve. That kind of claim demands rigorous testing, alternative explanations must be explored, observational biases must be ruled out, and the data must be examined from every angle to ensure that we are not seeing patterns where none exist. This is how science works. It is slow and careful, built on a foundation of skepticism and evidence. But the evidence continues to accumulate. New trans-Neptunian objects are discovered regularly, and many of them fit the pattern predicted by the Planet 9 hypothesis. Computer simulations show that a planet with the right mass, distance, and orbital characteristics could produce all of the observed phenomena, and while no one has yet found the planet itself, the fact that its existence is supported by multiple independent lines of evidence gives the hypothesis weight. It is not proof, not yet, but it is compelling enough that major observatories around the world have dedicated significant resources to the search. The clues are there, scattered across the dark frontier of the outer solar system, like pieces of a puzzle waiting to be assembled. They whisper of something massive and hidden, something that moves through the cold and the silence, shaping the paths of smaller worlds, influencing the structure of the solar system in ways we are only beginning to understand. Whether that something is Planet 9 or some other phenomenon we have not yet imagined, the mystery remains, and it is in that mystery, in the uncertainty and the search for answers, that science finds its purpose. We do not know what is out there, but we are looking. We are asking questions, testing hypotheses, gathering data, and one day, perhaps soon, perhaps not for many years, we might finally see what has been hiding in the dark all along. If Planet 9 truly exists, what kind of world would it be? This is not an easy question to answer because we have never seen it, and everything we think we know is based on inference and mathematical modelling, but that does not mean we are left entirely in the dark. The same calculations that suggest the planet exists also tell us something about its nature, its size, its orbit, its composition, and the strange, lonely conditions that define its existence. It would be a world unlike any in the inner solar system, a place where the familiar rules of temperature and light break down, where the sun is little more than a distant point, and where time moves on a scale that dwarfs human experience. Let us start with size. Based on the gravitational effects that Planet 9 appears to have on other objects, astronomers estimate that it would be a super-Earth, a type of planet larger than Earth but smaller than the ice giants Uranus and Neptune. Current models suggest its mass would be somewhere between 5 and 10 times that of Earth. That would make it smaller than Neptune, which is about 17 times Earth's mass, but significantly larger than our own world. Its size is important because it tells us something about its formation and composition. A planet this large could not be made entirely of rock like Earth. It would likely have a substantial envelope of gases, hydrogen and helium captured during the early days of the solar system, when these elements were abundant in the protoplanetary disk. Beneath that gaseous envelope, there might be a core of rock and ice, compressed under immense pressure. But unlike the gas giants of the inner solar system, Planet 9 would be cold. Extraordinarily cold. Its distance from the sun would place it far beyond the reach of any meaningful warmth. At 200 times Earth's distance from the sun, the average distance predicted for Planet 9's closest approach, sunlight would be 10,000 times weaker than it is here on Earth. At its farthest point, 1,200 times Earth's distance from the sun, that light would be 1,000,000 times weaker. The temperature on its surface, or rather in its upper atmosphere, since a super-Earth of this type might not have a solid surface in the way we usually think of one, would hover around minus 220 degrees Celsius, just 50 degrees above absolute zero. At those temperatures, even gases like nitrogen and methane would freeze solid. Any atmosphere that existed would collapse, falling as snow and ice onto the surface below. The world would be locked in an eternal deep freeze, dark and still, with no weather, no wind, no movement except the slow drift of cosmic particles passing through. The orbit of Planet 9, if the models are correct, would be highly elliptical, shaped more like a stretched oval than a circle. This is unusual. Most planets in the solar system orbit in roughly circular paths, a consequence of the way planetary systems form from rotating disks of material. But Planet 9's orbit would be different. It would swing close to the sun, relatively speaking, and then drift far out into the darkness before returning again. One complete orbit, 1 year on Planet 9, would take somewhere between 10,000 and 20,000 Earth years. To put that in perspective, the last time Planet 9 was at its closest point to the sun, if it is near that point now, human civilization might not have existed yet. The pyramids of Egypt might not have been built. Ice sheets might have covered much of North America and Europe. And by the time it returns to that same point in its orbit, everything we know, every culture, every nation, every person alive today, will be long gone. Because of this long orbital period, Planet 9 moves slowly through space. Not slowly compared to human speeds, of course, but slowly compared to the inner planets. Earth orbits the Sun at about 30 kilometers per second. Neptune, the slowest of the known planets, moves at about 5 kilometers per second. Planet 9, at its most distant point, might be moving at less than 1 kilometer per second, drifting lazily through the void like a ship becalmed on a cosmic ocean. This slow motion is part of what makes it so difficult to find. Astronomers looking for new objects in the sky often rely on detecting movement. They take multiple images of the same region of space over several nights and look for points of light that shift position relative to the background stars. But if an object is moving very slowly, that shift is tiny, almost imperceptible, and it can be easily missed or mistaken for noise in the data. If Planet 9 has moons, and it very well might, they would be frozen worlds in their own right, orbiting a planet that itself orbits in darkness. These moons would never see the sun as anything more than a bright star. They would be locked in orbit around their primary, their surfaces sculpted by ancient impacts, their skies filled with the faint glow of distant starlight. If any of these moons had atmospheres long ago, those atmospheres would be gone now, lost to space or frozen onto the surface. They would be geologically dead, places where nothing has changed for billions of years except the slow accumulation of impact craters and the patient work of cosmic radiation breaking down surface materials atom by atom. What would the sky look like from Planet 9? If you could somehow stand on its surface or float in its upper atmosphere, protected from the cold and the vacuum, what would you see? The sun would still be the brightest object in the sky, but it would not dominate the view the way it does from Earth. It would appear as a brilliant point, brighter than any star but not much larger. It would cast light, enough perhaps to read by if you were patient, but it would not provide warmth. The rest of the sky would be filled with stars, more stars than you can see from Earth because there would be no atmosphere to scatter their light, no light pollution to wash them out. The Milky Way would stretch across the heavens in a river of pale light, and if you looked carefully you might be able to see some of the brighter planets of the inner solar system, Venus perhaps, or Jupiter, though they would be so distant that they would appear as little more than faint points among the multitude of stars. The composition of Planet 9 is another mystery wrapped inside the larger mystery of its existence. If it is a super-Earth with a gaseous envelope, that envelope is probably made of hydrogen and helium, the lightest and most abundant elements in the universe. These gases would have been captured from the protoplanetary disk when the planet was young, when it formed in a region where gas was still plentiful. But over billions of years, some of that atmosphere might have been lost. The planet's gravity, while strong, is not as strong as that of Jupiter or Saturn. Solar wind and radiation, even at such great distances, could slowly strip away lighter gases. What remains might be a thin, cold shell, a ghost of the thick atmosphere the planet might once have had. Beneath that, there could be layers of ice, water ice, methane ice, ammonia ice, surrounding a rocky core. This structure would be similar to Uranus and Neptune, though smaller and colder. But all of this is speculation. We do not know if Planet 9 exists. We do not know its exact size or composition. We do not even know where it is. What we have are models, simulations, predictions based on the gravitational effects we observe. These models are powerful. They have been tested and refined. They are consistent with the data, but they are not the same as direct observation. Until someone finds Planet 9, until a telescope captures its faint reflected light and we can measure its properties directly, it remains a theoretical construct, a mathematical ghost haunting the equations of celestial mechanics. And that is part of what makes this search so compelling. We are not looking for something we know is there. We are looking for something that should be there if our understanding of gravity and orbital dynamics is correct. We are testing the limits of our theories, pushing our instruments to the edge of their capabilities, searching for a signal so faint that it could easily be lost in the noise. It is detective work on a cosmic scale, and the prize, if it is ever found, would be one of the great discoveries of our time. Finding a planet is not as simple as pointing a telescope at the sky and waiting for something to appear. The universe is vast, and even our own solar system, which is just a tiny corner of that vastness, contains enough space to hide entire worlds. The search for Planet 9 is not a matter of luck, but of strategy, patience, and the careful application of science and technology. It is a search that has been going on for years now, involving some of the most powerful telescopes on Earth and the dedicated efforts of astronomers who spend night after night scanning the darkness, hoping for a glimpse of something that might not even be there. The challenge of finding Planet 9 comes down to three main problems. First, it is very far away. Second, it is very faint. And third, we do not know exactly where to look. Let us consider each of these challenges in turn, because understanding them helps us appreciate just how difficult this search really is. Distance is the first obstacle. If Planet 9 orbits at an average distance of several hundred times the Earth-Sun distance, it is farther from the Sun than any object we have ever imaged in our solar system, except for the most distant comets. At that distance, even a relatively large planet would appear incredibly small in a telescope. The angular size, the apparent diameter as seen from Earth, would be measured in tiny fractions of an arcsecond. To put that in perspective, an arcsecond is 1/36th of a degree. The full moon, by comparison, is about half a degree across, or 1800 arcseconds. Planet 9, even through the most powerful telescopes, would appear as a point of light, indistinguishable from a star except for one crucial difference: it would move. That brings us to the second challenge: brightness, or rather the lack of it. Planets do not produce their own light. They shine by reflecting sunlight, but the amount of sunlight that reaches Planet 9 is minuscule, and the amount that reflects back toward Earth is even smaller. Brightness decreases with the square of the distance, so an object twice as far from the Sun receives 1/4 as much light. Planet 9 is not twice as far as Neptune, it is 10 times farther, or more. That means it receives 100 times less sunlight than Neptune, or even less depending on where it is in its orbit. And Neptune is already so far from the Sun that it is barely visible in binoculars. Planet 9, if it exists, would be vastly fainter, right at the edge of what even the largest ground-based telescopes can detect. In fact, it might be so faint that only a handful of telescopes in the world are powerful enough to see it at all. The third problem is the most frustrating. We do not know where it is. The models tell us roughly where Planet 9 should be in terms of its orbit, but an orbit is not a single point. It is a vast ellipse stretching across billions of kilometers of space. At any given moment, the planet could be anywhere along that path, and because its orbital period is so long, it moves very slowly, making it difficult to predict its current position based on its past influence. To make matters worse, the sky is enormous. Even if we narrow down the search to a specific region, that region still contains billions of stars, galaxies, and other background objects that must be carefully examined to find the one faint, moving point that might be Planet 9. So, how do astronomers approach this challenge? The first step is to narrow down the search area as much as possible using the available data. The orbits of the trans-Neptunian objects that seem to be influenced by Planet 9 provide clues. By studying the clustering of those orbits and running computer simulations, researchers can estimate where Planet 9 is most likely to be. These simulations suggest that the planet is probably in a particular region of the sky, though that region is still large enough to require years of observations to cover completely. Once the search area has been defined, astronomers begin the painstaking process of surveying that region. This involves taking images of the sky over multiple nights and comparing them to look for objects that have moved. The technique is called astrometry, and it has been used for centuries to discover everything from asteroids to distant stars with planets. But finding something as faint as Planet 9 requires images of exceptional quality, long exposures to gather as much light as possible, and sophisticated software to analyze the data and identify moving objects. Several major telescopes are currently involved in the search. The Subaru telescope in Hawaii, one of the largest optical telescopes in the world, has been used extensively to scan the regions where Planet 9 might be. Subaru's wide field of view allows it to cover large areas of sky in a relatively short amount of time, making it ideal for this kind of survey work. Other facilities, including telescopes in Chile and California, have also contributed to the effort, each one adding to the growing catalogue of distant objects and slowly eliminating areas where Planet 9 is not. But there is a limit to what ground-based telescopes can achieve. The atmosphere of Earth, while transparent enough to allow us to see the stars, is not perfectly stable. It shimmers and distorts light, blurring the images and making it difficult to detect faint objects. Adaptive optics, a technology that uses deformable mirrors to compensate for atmospheric distortion, helps to some extent, but there is only so much that can be done from the ground. This is one reason why astronomers are excited about future space-based telescopes, instruments that will operate above the atmosphere and be able to detect fainter objects with greater clarity. Missions like the James Webb Space Telescope, while primarily designed for other purposes, have the potential to contribute to the search if Planet 9 is bright enough and if its location can be narrowed down further. Another approach involves looking not for the planet itself, but for its effects. If Planet 9 exists, its gravity will continue to influence other objects in the outer solar system. By discovering more trans-Neptunian objects and studying their orbits, astronomers can refine their models and get a better sense of where the planet should be. Each new discovery is another piece of the puzzle, another constraint on the possible properties and location of the hidden world. This indirect method is slower, but it has the advantage of being less dependent on luck. Even if Planet 9 is currently in a part of its orbit where it is too faint to detect, the evidence for its existence will continue to accumulate as more objects are found and their orbits are analysed. There is also the possibility that Planet 9 has already been photographed but not recognised. Sky surveys, automated programs that photograph large areas of the sky repeatedly, have captured billions of images over the years. Somewhere in those archives there might be a faint dot that moves slightly from one image to the next, a dot that was dismissed as noise or a cosmic ray or a distant asteroid. Researchers are now going back through old data, reanalyzing images with modern software and new search algorithms, hoping to find something that was missed the first time. It is tedious work, but it has paid off before. Pluto, for example, was discovered by comparing photographic plates, and many other objects in the solar system have been found in archival data years after the images were taken. The search for Planet 9 is as much a test of human persistence as it is a test of technology. It requires patience, the willingness to spend years looking at data that might reveal nothing, the discipline to carefully rule out false positives, and the optimism to keep searching even when the odds seem long. It is the kind of work that does not make headlines every day, but when it succeeds, when that faint point of light is finally found and confirmed to be moving in the way the models predict, it will be a moment of profound discovery. It will be proof that even in our own cosmic neighborhood, there are still mysteries waiting to be solved, and that the universe still has surprises for those who are willing to look carefully enough. But until that moment comes, the search continues. Night after night, telescopes turn their gaze toward the outer solar system. Cameras capture photons that have traveled for hours across the void, and astronomers analyze the data, looking for the one signal that does not quite fit, the one faint object that moves when everything else is still. Somewhere out there in the dark, Planet 9 might be waiting, unaware that curious minds on a small blue world are searching for it, trying to bring it into the light. Gravity is the invisible hand that shapes the cosmos. It is the force that holds planets in orbit around stars, binds galaxies together across unimaginable distances, and governs the motion of everything from the smallest asteroid to the largest black hole. We cannot see gravity, we cannot touch it or hear it, but we can see its effects. The way it bends the paths of objects, the way it pulls matter together, the way it writes the story of the universe in the language of motion and mass. And it is through gravity, through the careful study of how objects move and why they move the way they do, that astronomers hope to finally prove the existence of Planet 9. The science of detecting objects through their gravitational influence is not new. It is, in fact, one of the oldest tools in the astronomer's toolkit. Long before we had the technology to image distant planets directly, we could infer their presence by watching how they affected other objects. Neptune itself, the 8th planet in the solar system, was discovered this way. In the mid-19th century, astronomers noticed that Uranus was not quite where it should be. Its orbit was being perturbed, pulled slightly off course by something unseen. By carefully analysing those perturbations, mathematicians were able to predict the location of a new planet, and when telescopes were pointed at that location, Neptune was found almost exactly where the calculations said it would be. It was a triumph of mathematics and a demonstration of the power of gravity to reveal hidden worlds. Planet 9, if it exists, would be discovered through a similar process, though the challenge is far greater now than it was in the 19th century. Neptune was relatively close, orbiting at a distance where its effects on Uranus were strong and relatively easy to measure. Planet 9, by contrast, is so far away that its influence on other objects is subtle, a gentle tug spread out over millions of years. Detecting that tug requires not just careful measurements, but an understanding of how gravity works over vast timescales and enormous distances. Let us consider how gravity shapes orbits. When a small object, a trans-Neptunian body for example, orbits the Sun, its path is determined primarily by the Sun's gravity. The Sun is so massive compared to everything else in the solar system that it dominates the gravitational landscape, but the Sun is not the only gravitational influence. The planets, though much smaller, also exert their own gravitational pull. When a small object passes near a planet, that planet's gravity tugs on it, changing its speed and direction slightly. Over time, these small changes accumulate. An orbit that was once circular might become elliptical. An orbit that was aligned with the plane of the solar system might become tilted. These are called perturbations, and they are the fingerprints of gravitational influence. In the case of the trans-Neptunian objects whose orbits seem to point toward the existence of Planet 9, the perturbations are subtle but consistent. Their orbits are not just randomly elliptical or randomly tilted, they are aligned in a way that suggests a common cause. When researchers run computer simulations, modeling the motion of these objects under the influence of the known planets, they find that the observed clustering does not occur. The orbits spread out randomly, just as you would expect if only the known planets were present. But when they add a ninth planet to the simulation, a massive object in a distant eccentric orbit, the clustering appears. The orbits of the small objects begin to align, just as they do in reality. This is not proof in the strictest sense, but it is strong evidence. It is the mathematical equivalent of seeing footprints in the snow and inferring that someone walked there, even if you did not see them yourself. The gravitational influence of Planet 9 would work slowly, unlike the rapid changes that occur when a comet passes close to Jupiter and is flung out of the solar system. The perturbations caused by Planet 9 would accumulate over millions of years. Each time one of the distant trans-Neptunian objects passes through the region of space where Planet 9's gravity is strongest, it is nudged slightly. The change in its orbit might be imperceptible at first, but over many orbits, over millions of years, those small nudges add up. Eventually, the object's orbit is significantly different from what it would have been without Planet 9's influence. This process is called secular perturbation, and it is one of the key mechanisms by which distant planets can shape the architecture of a planetary system without directly colliding with or closely approaching other objects. It is a subtle form of gravitational sculpting, and it leaves behind patterns that can persist for billions of years. The clustering of orbits that we see in the trans-Neptunian population is exactly the kind of pattern that secular perturbations would produce. It is the signature of a distant, massive object whose gravity has been quietly shaping the outer solar system since the planets first formed. But gravity does more than just change orbits. It can also create them. Some researchers believe that Planet 9 itself might have been responsible for scattering some of the trans-Neptunian objects into their current distant orbits. Early in the solar system's history, when the planets were still migrating and jostling for position, a large planet in the outer solar system could have flung smaller objects outward, sending them into the distant, elliptical paths they follow today. If that planet was later pushed into a more distant orbit itself, perhaps by gravitational interactions with Jupiter or Saturn, it would have left behind a population of scattered objects whose orbits bear the imprint of that ancient encounter. There is also the question of resonance, a phenomenon that occurs when two orbiting objects have periods that are related by a simple ratio. Resonances are common in the solar system. Pluto and Neptune, as mentioned earlier, are in a 3-to-2 resonance. Many of Jupiter's moons are locked in resonances with one another. These relationships are stable and can persist for billions of years. Some of the trans-Neptunian objects appear to be in resonance with something unseen, something whose orbital period matches the predictions for Planet 9. If these resonances are real and not just coincidental, they would be powerful evidence for the planet's existence, because resonances form only through long-term gravitational interactions between massive objects. All of this gravitational detective work relies on precise measurements and sophisticated computer models. Astronomers must know the orbits of the trans-Neptunian objects with great accuracy, which means observing them over many years to see how they move. They must account for the gravitational effects of all the known planets, making sure that what they are seeing is not just the result of Neptune's gravity or some other known influence. and they must test their models rigorously, varying the parameters, trying different configurations, and seeing what works and what does not. It is painstaking work, and it requires both technical skill and creative thinking, but the effort is worthwhile because gravity never lies. It is one of the most fundamental forces in the universe, and it follows rules that we understand very well. If the mathematical models say that a massive planet is the best explanation for the observed perturbations, then there is a good chance that such a planet exists. Gravity is the thread that connects the seen and the unseen, the bridge between observation and discovery. And as astronomers continue to refine their understanding of how gravity shapes the outer solar system, they move closer to finding the hidden world that has eluded them for so long. If Planet 9 is real, if it truly orbits in the cold and darkness beyond Neptune, then its existence raises profound questions about how our solar system formed and how it has evolved over the past 4.5 billion years. The presence of a massive planet in such a distant, eccentric orbit does not fit neatly into the traditional story of planetary formation. It is an anomaly, a puzzle piece that does not quite match the others, and that makes it both fascinating and troubling. Because if Planet 9 is there, it means that something unusual happened in the early solar system, something that disrupted the orderly process planet formation and left behind a hidden giant as evidence. The traditional model of how planets form is relatively straightforward, at least in broad strokes. A star is born from a cloud of gas and dust, and around that star, the remaining material settles into a rotating disk. Within that disk, particles collide and stick together, gradually building up larger and larger objects. Dust becomes pebbles, pebbles become boulders, boulders become planetesimals, and planetesimals, if they are lucky and if they are in the right place, become planets. This process happens over millions of years, and it produces a planetary system that is relatively flat and relatively orderly, with planets orbiting in roughly circular paths all going in the same direction. But Planet 9, if it exists, does not fit this picture. Its orbit is too elliptical, too tilted, too distant. It is not where a planet should be if it formed in place from the protoplanetary disk. So the question becomes, where did it come from? How did it end up in such an unusual orbit? There are a few possibilities, each with its own implications and its own set of challenges. One possibility is that Planet 9 formed much closer to the Sun, in the region where the giant planets Jupiter, Saturn, Uranus and Neptune now orbit. In the early solar system, this region was crowded with planetary embryos, large objects that were in the process of becoming planets. Most of these embryos either merged with one another to form the planets we know today, or were ejected from the solar system entirely by gravitational interactions with the growing giants. But it is possible that one of these embryos, an object perhaps 5 or 10 times the mass of Earth, was scattered outward rather than inward or entirely out of the solar system. If it was flung into a distant, eccentric orbit by a close encounter with Jupiter or Saturn, it could have ended up where we think Planet 9 is today. This scenario has the advantage of explaining why Planet 9 is so massive. In the outer regions of the protoplanetary disk, where the planet presumably is now, there was not enough material to build a world that large. The density of gas and dust was too low, and the timescales were too long. But closer to the Sun, in the region of the giant planets, there was plenty of material, and planets could grow quickly. If Planet 9 formed there and was later scattered outward, it would have retained its mass while ending up in a place where such a massive object should not exist. But there is a problem with this idea. Scattering a planet into a stable, distant orbit is not easy. Most objects that are scattered by the giant planets are either ejected from the solar system entirely or sent into orbits that eventually bring them back close to the Sun, where they are scattered again or collide with something. Getting an object into a stable orbit at hundreds of times the Earth-Sun distance requires a very specific set of conditions, and it is not clear that those conditions could have been met during the chaotic early days of the solar system. Some researchers have suggested that interactions with other stars, passing close to the young Sun during the time when it was still part of a stellar nursery, could have helped to stabilize Planet 9's orbit. But this is speculative, and it adds another layer of complexity to an already complicated story. Another possibility is that Planet 9 did not form in our solar system at all. It might be a rogue planet, a world that formed around another star and was later captured by the Sun's gravity. Rogue planets are thought to be common in the galaxy. Simulations of planetary system formation suggest that many planets are ejected from their home systems during the chaotic early period of gravitational interactions, and these orphaned worlds wander through space, unbound to any star. If one of these rogue planets happened to pass close to the Sun at just the right distance and just the right speed, it could have been captured into orbit. The orbit would naturally be eccentric and tilted because the planet's motion would not have been aligned with the solar system's disk. This idea is intriguing because it would make Planet 9 not just an unusual planet, but an entirely foreign object, a visitor from another stellar system that has become a permanent part of ours. It would also help to explain some of the planet's unusual properties, but capture is a difficult process. The conditions have to be just right, and the probability of capturing a planet as massive as Planet 9 is low. Most rogue planets that pass through the solar system would either be flung back out into space by the gravity of the Sun and the giant planets, or would collide with something, which is even less likely given the vast distances involved. A third possibility, and one that has gained attention in recent years, is that Planet 9 formed where it is now, but in a protoplanetary disk that was much more massive than the one we usually think of. If the outer regions of the disk contained more material than current models suggest, it might have been possible for a super-Earth to form at such a great distance. This would require rethinking some of our assumptions about the early solar system, but it is not impossible. The problem is that we do not have direct evidence of what the outer disk was like 4.5 billion years ago. We can only infer its properties from the planets and other objects that exist today, and those clues are limited. Regardless of how Planet 9 formed or how it ended up in its current orbit, its presence, if confirmed, would force astronomers to reconsider their understanding of planetary system dynamics. It would suggest that the early solar system was more chaotic and more complicated than we realized, with planets moving, colliding, and being scattered in ways that left lasting marks on the architecture we see today. It would also raise questions about other planetary systems. If our solar system can hide a massive planet in its outer reaches, how many other systems have similar hidden worlds? Are distant, eccentric planets common, or is Planet 9 a rare anomaly? There is also the question of what Planet 9's existence would mean for the long-term stability of the solar system. The orbits of the planets we know about are stable over billions of years. They do not collide with one another or spiral into the Sun, but that stability is not absolute. It is the result of a delicate balance of gravitational forces, and adding a new massive planet to the system could, in principle, change that balance. Simulations suggest that Planet 9's orbit, if the current models are correct, would not destabilize the inner planets. Its influence is too weak and too distant, but it could affect the outer solar system in subtle ways, changing the orbits of smaller objects and perhaps even influencing the flow of comets from the Oort cloud, the vast shell of icy bodies that surrounds the solar system at its farthest edges. In thinking about Planet 9, we are not just thinking about a single object. We are thinking about the history of our solar system, the processes that shaped it, and the forces that continue to govern its evolution. We are asking how much we really know about the place we call home and what surprises might still be waiting to be discovered. Every planet, every moon, every asteroid is a piece of a larger puzzle, and Planet 9, if it is real, is a piece that we did not even know was missing until recently. Finding it would not just complete the puzzle, it would change the picture we thought we were assembling. The word terrifying appears in the title of this exploration for a reason. There is something unsettling about the idea of a massive, unseen planet lurking in the outer darkness of our solar system, quietly exerting its gravitational influence on everything around it. It is not that Planet 9, if it exists, poses an immediate danger. It is not going to suddenly appear in the inner solar system and crash into Earth. Its orbit keeps it far, far away, and the timescales on which it moves are so long that any changes it might cause would unfold over millions of years. But the fact that such a planet could exist without our knowledge, the fact that our solar system might be shaped by forces we have not yet fully accounted for, raises questions about stability, about predictability, and about the hidden dangers that might be drifting through the void. The primary concern, such as it is, revolves around gravity. Planet 9, with its estimated mass of 5 to 10 Earths, has a gravitational field strong enough to influence objects across vast distances. It is this influence that gives us the clues to its existence, the clustering of orbits, the tilting of paths, the slow reshaping of the outer solar system. But gravity is not selective. It affects everything within its reach, and that includes not just the distant trans-Neptunian objects, but also comets, asteroids, and anything else that drifts too close. Over millions of years, Planet Nine's gravity could nudge some of these objects into new orbits, and in rare cases, those new orbits could bring them closer to the Sun, closer to the inner solar system, closer to Earth. This is not a new phenomenon. Comets and asteroids have been deflected into Earth-crossing orbits throughout the history of the solar system. It is how impact craters form. It is how extinction events happen. The dinosaurs, most famously, were wiped out by the impact of a large asteroid or comet 66 million years ago. That impact was not caused by Planet Nine, of course, or if it was, we have no way of knowing, but it illustrates the point that the solar system is not a static place. Objects move, orbits change, and occasionally something that was once safely distant finds itself on a collision course with Earth. Planet Nine's role in this process, if it exists, would be indirect. It would not launch objects directly at Earth. What it would do is alter the orbits of objects in the outer solar system, some of which might eventually wander inward. The process would be slow, playing out over timescales measured in millions of years. A comet in a stable orbit beyond Neptune might, after repeated gravitational nudges from Planet Nine, find itself on a path that takes it closer to the Sun. Once it is in the inner solar system, it could interact with the gravity of the giant planets, Jupiter and Saturn, which could further change its orbit. Eventually, after a long and chaotic journey, it might end up on a trajectory that crosses Earth's path. This is, admittedly, a low-probability scenario. The solar system is vast, and space is mostly empty. The chances of any particular comet or asteroid hitting Earth are extremely small, even over millions of years. But the concern is not about any one object. It is about the cumulative effect of Planet Nine's influence over billions of years. If Planet Nine has been quietly reshaping the outer solar system since the planets first formed, it might have increased the overall number of objects that have been sent inward over time. Some of those objects might have already collided with Earth in the distant past, contributing to the impacts that scarred the early surface of our planet. Others might be on their way now, or they might arrive in the distant future, long after human civilization has either adapted to the threat or ceased to exist. There is also the question of the Oort cloud, the vast, spherical shell of icy bodies that surrounds the solar system at distances of tens of thousands of times the Earth-Sun distance. The Oort cloud is thought to be the source of long-period comets, those comets that take thousands or millions of years to complete one orbit around the Sun. These comets are mostly dormant, drifting in the cold darkness, but occasionally something disturbs them. A passing star, a gravitational wave from a distant galactic event, or perhaps the influence of a massive planet like Planet Nine. When disturbed, a comet can be nudged out of the Oort cloud and sent falling toward the inner solar system, where the Sun's heat vaporizes its ice and creates the spectacular tail that makes comets so visually striking. If Planet Nine exists, and if its orbit takes it through or near the inner edge of the Oort cloud, it could be a significant source of cometary disturbances. Over millions of years, its gravity could send a steady stream of comets inward, increasing the rate at which these objects pass through the inner solar system. Most would miss Earth, of course, but a higher rate of comets means a higher probability that one of them will eventually cross our path. This is not an immediate threat. Even if Planet Nine is perturbing the Oort cloud right now, the effects would not be felt for thousands or millions of years. But it is a reminder that the solar system is a dynamic place and that distant objects can have far-reaching effects. Beyond the physical threat of impacts, there is a more philosophical kind of unease that comes with the idea of Planet Nine. We like to think that we understand our cosmic neighborhood, that we have mapped it, measured it, and tamed it with our knowledge. The discovery of a massive planet that has been hiding in plain sight for all of human history would be a humbling reminder that our understanding is incomplete. It would force us to confront the fact that even in the 21st century, with all of our technology and all of our science, there are still profound unknowns lurking at the edges of our awareness. If we can miss a planet in our own solar system, what else might we be missing? What other dangers? What other surprises might be waiting to be discovered? There is also the question of long-term stability. The solar system, as we currently understand it, is stable over timescales of billions of years. The orbits of the planets are predictable. They do not collide. They do not spiral into the Sun. This stability is the result of a delicate balance of gravitational forces, and any change to that balance, such as the addition of a new massive planet, could in principle lead to instability. Simulations suggest that Planet Nine's orbit would not destabilize the inner planets, but those simulations are based on models that make certain assumptions. If those assumptions are wrong, if there is something about Planet Nine's orbit or mass that we have not accounted for, the long-term consequences could be more significant. It is important to emphasize that none of this is a reason for alarm. Planet Nine, if it exists, is not a doomsday scenario. It is not hurtling toward us. It is not about to knock Earth out of its orbit. The timescales involved are so long and the distances so vast that any effects it might have on the inner solar system would be negligible on human timescales. But the presence of such a planet would remind us that the universe does not care about our comfort or our sense of security. It operates according to its own rules, and those rules sometimes produce outcomes that are unexpected, unsettling, or even dangerous. In the end, the terror of Planet Nine is not the terror of immediate catastrophe. It is the terror of the unknown, the realization that even in a place we thought we knew, there might be something massive and powerful that we have overlooked. It is the understanding that the solar system is not a finished painting but a work in progress, shaped by forces that are still active, still moving, still capable of surprising us. And it is the recognition that we are small, fragile, and dependent on a stability that is not guaranteed, that could be disrupted by events we cannot foresee or control. For all the evidence that seems to point toward the existence of Planet Nine, it is important to remember that science is not about certainty. It is about probabilities, about testing hypotheses, and about being willing to consider alternative explanations. The clustering of trans-Neptunian orbits is real. The gravitational anomalies are real. But that does not necessarily mean that Planet Nine is real. There are other ways to explain the observations, and some of them do not require a massive hidden planet at all. These alternative theories are worth exploring, not because they are more likely to be correct, but because considering them is part of the scientific process. It is how we avoid jumping to conclusions and how we ensure that our understanding is built on solid ground. One of the most straightforward alternative explanations is observational bias. This is the idea that the clustering of orbits is not real, but is instead an artifact of the way we search for trans-Neptunian objects. Telescopes can only observe certain parts of the sky, and they are better at finding objects in some regions than in others. If astronomers have been preferentially searching areas where the sky is clearer, where the background stars are less dense, or where previous discoveries have been made, they might be more likely to find objects in those areas. This could create the appearance of clustering even if the actual distribution of objects is random. This is a serious concern, and researchers have spent a lot of time trying to determine whether observational bias can fully explain what we see. The answer seems to be no, at least not completely. While bias is certainly present to some degree, statistical analyses suggest that the clustering is stronger than bias alone can account for. The odds of the observed alignment happening by chance are low enough that most researchers believe there is a real physical cause, even if we do not yet know what that cause is. But the possibility remains, and it is a reminder that what we observe is not always the same as what is truly out there. Another alternative explanation involves the collective gravity of smaller objects. Instead of one massive planet, perhaps there are many smaller objects, each with its own gravitational field, that together produce the effects we attribute to Planet Nine. If the outer solar system is more densely populated with unseen objects than we realize, their combined gravity could, in principle, create the kind of perturbations we observe. This idea has the advantage of not requiring a single massive object, which would solve the problem of how such a planet ended up in such an unusual orbit. But it has its own challenges. To produce the observed effects, there would need to be a lot of mass distributed in a very specific way, and it is not clear that such a configuration is likely or stable over billions of years. A more radical alternative involves modifying our understanding of gravity itself. The laws of gravity, as described by Isaac Newton and later refined by Albert Einstein, have been tested extensively and have proven to be extraordinarily accurate in describing the motion of objects in the solar system and beyond. But they are not perfect. At very large distances or very small scales, there are hints that gravity might behave slightly differently than we expect. Some physicists have proposed modifications to the theory of gravity that would alter the strength or behavior of gravitational forces under certain conditions. If one of these modified theories is correct, it is possible that the clustering of trans-Neptunian orbits could be explained without invoking a hidden planet. This idea is intriguing, but it is also highly speculative. Modified gravity theories have been proposed to explain other phenomena, such as the rotation curves of galaxies or the accelerating expansion of the universe, but none of them have been conclusively proven. And even if gravity does behave differently at large distances, it is not clear that the specific modifications required to explain the trans-Neptunian orbits are consistent with the modifications needed to explain other observations. Most physicists remain skeptical, and they prefer explanations that do not require rewriting fundamental physics unless absolutely necessary. There is also the possibility that the clustering is real but temporary. Orbital dynamics can produce transient patterns, alignments that last for a while and then disperse. If the trans-Neptunian objects are currently in a configuration that happens to look clustered but will spread out again in the future, we might be seeing a snapshot of a temporary state rather than evidence of a long-term influence. Testing this idea requires long-term observations, tracking the motion of these objects over decades or even centuries to see whether the clustering persists or fades. Some researchers have also suggested that the clustering could be the result of interactions with passing stars. The Sun is not alone in space. It is part of the Milky Way galaxy, and like all stars in the galaxy, it moves through a dynamic environment filled with other stars, gas clouds, and various forms of matter. Occasionally, a star passes relatively close to the solar system, and its gravity can disturb the orbits of distant objects. If a star passed through or near the Oort cloud, or the scattered disk millions of years ago, it could have perturbed the orbits of trans-Neptunian objects in a way that created the patterns we see today. This would not require Planet 9 at all, but this explanation also has problems. Stellar encounters are rare, and the effects of such encounters tend to be short-lived on astronomical timescales. The clustering we observe seems to be stable and persistent, which suggests that whatever is causing it is still present and still active. A passing star would have moved on long ago, and its influence would have faded. Unless there is ongoing perturbation from something currently in the solar system, it is hard to explain why the clustering has lasted this long. Each of these alternative explanations has strengths and weaknesses, and each one deserves serious consideration. Science is not about picking the explanation that sounds best or the one that is most exciting. It is about following the evidence wherever it leads, testing each hypothesis rigorously, and being willing to change our minds when new data becomes available. Right now, the Planet 9 hypothesis is the leading explanation for the observed clustering because it fits the data well and because it makes testable predictions. But it is not the only explanation, and it is important to remain open to other possibilities. This openness is not a weakness, it is a strength. It is what separates science from dogma. By considering alternatives, by challenging our assumptions, and by demanding rigorous evidence, we ensure that our conclusions are as solid as possible. If Planet 9 is real, the evidence will continue to accumulate until it becomes undeniable. If it is not real, then one of the alternative explanations will eventually prove to be correct, or perhaps an entirely new explanation will emerge that no one has thought of yet. Either way, the search for answers continues, guided not by the desire to be right, but by the desire to understand. Beyond Neptune, beyond the scattered disk, beyond even the hypothetical orbit of Planet 9, there lies a realm of space so vast and so dark that it challenges the imagination. This is the outer edge of the solar system, a place where the sun's light is so faint that it barely registers, where temperatures are measured in degrees above absolute zero, and where time seems to move at a different pace. It is here, in this cold and silent frontier, that some of the solar system's most mysterious objects reside, and it is here that the true boundaries of our cosmic neighbourhood remain uncertain, undefined, and largely unexplored. The outermost known region of the solar system is the Oort cloud, a vast, spherical shell of icy bodies that surrounds the Sun at distances ranging from a few thousand to as much as 100,000 times the Earth-Sun distance. The Oort cloud has never been directly observed. We know it exists because of the comets that occasionally fall inward from those distant reaches, their long elliptical orbits carrying them through the inner solar system, where they flare into visibility as the Sun's heat vaporizes their icy surfaces. These comets are messengers from the deep cold, remnants of the material that formed the planets but never accreted into anything larger, scattered outward by the gravity of the giant planets billions of years ago. The Oort cloud marks the gravitational boundary of the solar system, the region where the sun's gravity is still dominant but only barely. Beyond the Oort cloud, the gravitational influence of other stars begins to compete, and the line between what belongs to the solar system and what belongs to interstellar space becomes blurred. It is a frontier that no spacecraft has ever crossed. Voyager 1 and Voyager 2, the farthest human-made objects, have left the heliosphere, the bubble of charged particles blown outward by the solar wind, but they are still thousands of years away from reaching the inner edge of the Oort cloud. And even if they could travel that far, they would find a region so sparsely populated that the chances of passing close to any individual object are vanishingly small. If Planet 9 exists, its orbit likely takes it through the inner regions of the Oort cloud, making it a bridge between the known solar system and this distant, mysterious realm. Its gravity would interact with the comets and icy bodies that drift there, occasionally sending one of them on a long journey toward the sun. In this sense, Planet 9 would be not just a member of the solar system, but a sculptor of its outermost architecture, a force that shapes the flow of material between the deep cold and the relative warmth closer to the sun. But the Oort cloud is not the end. Even beyond that vast shell, there is more. Interstellar space is not empty. It is filled with gas, dust, and the occasional rogue planet or brown dwarf, objects that do not orbit any star but wander through the galaxy alone. Some of these objects might pass close to the solar system from time to time, their gravity briefly disturbing the Oort cloud or the scattered disk before they continue on their way. We do not know how common such encounters are, and we have never directly observed one happening, but they are part of the larger environment in which the solar system exists, a reminder that we are not isolated but embedded in a dynamic and ever-changing galaxy. The darkness of the outer solar system is not just an absence of light, it is a profound isolation, a place where the distances are so great that even travelling at the speed of light, a message from Earth would take hours or days to arrive. The cold is absolute, the silence complete. No wind stirs because there is no atmosphere. No sound carries because there is no medium for it to travel through. It is a place that exists at the edge of human comprehension, too vast to visit, too far to fully understand, and yet intimately connected to the world we live on. There is something humbling about contemplating these outer reaches. We are so accustomed to thinking of the solar system as a small, knowable place that it is easy to forget just how much of it lies beyond our direct experience. The inner solar system, the region where Earth, Mars, Venus, and Mercury orbit, is a tiny fraction of the whole. Even adding in the giant planets, Jupiter, Saturn, Uranus, and Neptune, we have only accounted for a small bubble at the centre of a vastly larger structure. The rest, the scattered disk, the Kuiper belt, the Oort cloud, and whatever lies beyond, is still largely unknown, explored only through mathematical models and the occasional lucky observation. Planet 9, if it is real, would be one of the few objects we know of that exists in this outer darkness, and studying it would give us a window into conditions and processes that we can barely imagine. What is it like out there, so far from the sun that years are measured in tens of thousands of Earth years? What happens to a planet when it is isolated from the warmth and light that define our own existence? Does it have weather? Does its surface crack and shift under the slow pull of tidal forces? Or is it simply frozen, dead, unchanging, a relic of the early solar system preserved in a state of perfect stillness? We do not know. We may not know for a very long time, but the questions themselves are valuable. They push us to think beyond the familiar, to imagine worlds and environments that are completely unlike our own, and to recognize that the universe is far stranger and more diverse than we might have guessed. Every planet, every moon, every distant icy body is a laboratory, a place where the laws of physics play out in unique ways, creating outcomes that we can study, learn from, and use to deepen our understanding of how the cosmos works. In this outer darkness, there is also beauty. Not the beauty of sunlight on water or the colours of a sunset, but the beauty of vastness, of silence, of the slow and patient unfolding of time. It is a beauty that does not demand attention, that does not shout or dazzle, but that rewards contemplation. To think about these distant places, to let your mind wander out into the cold and the dark, is to touch something profound, something that connects us to the larger universe and reminds us that we are part of a story far older and far larger than ourselves. And perhaps somewhere out there in that darkness, Planet 9 is waiting, not with intention, not with awareness, but simply existing, following its long, slow orbit, unaware that on a small world closer to the Sun, curious minds are searching for it. And maybe one day we will find it. Maybe one day a telescope will capture its faint light, and we will finally see what has been hidden for so long. And when that day comes, if it comes, we will look at the image and know that the solar system is a little less mysterious, a little more understood. But we will also know that beyond that new discovery, there will be more mysteries waiting, more questions to ask, more unknowns to explore, because that is the nature of the universe. It does not give up its secrets easily, and it never runs out of surprises. We have come a long way in this journey, from the strange clustering of distant orbits to the mathematical models that hint at a hidden world, from the challenges of searching for something so faint and so far to the philosophical questions raised by the possibility that our solar system might still hold profound unknowns. We have explored the evidence, considered the alternatives, and imagined what it might mean if Planet 9 is real. But now, as we near the end, it is worth stepping back and asking a broader question, one that goes beyond the specifics of this particular mystery. What does it mean to live with uncertainty? What does it mean to accept that there are things we do not know, might never know, and yet continue to search for answers anyway? Planet 9, whether it exists or not, is a symbol of that uncertainty. It represents the limits of our knowledge and the boundaries of our understanding. It reminds us that the universe does not owe us answers, that reality is not obligated to conform to our expectations, and that the process of discovery is often slow, frustrating, and incomplete. And yet, despite all of that, we keep looking. We keep asking questions. We keep building telescopes, running simulations, and analyzing data. Not because we are certain we will find what we are looking for, but because the search itself is meaningful. There is something deeply human about this impulse, this need to understand, to explore, to push against the edges of the known and see what lies beyond. It is the same impulse that drove ancient sailors to venture beyond the horizon, that sent explorers across continents and oceans, and that now propels our spacecraft into the depths of the solar system and beyond. It is not always rational. The odds of finding Planet 9 are uncertain. The resources required are significant, and even if it is found, the discovery will not change our daily lives in any immediate way. But we search anyway, because curiosity is part of what makes us who we are, and there is value in that search, even if it never leads to a definitive answer. The process of looking for Planet 9 has already taught us things about the outer solar system, about orbital dynamics, and about the techniques required to find faint, distant objects. It has forced us to refine our models, to question our assumptions, and to think carefully about what we think we know and why we think we know it. Even if Planet 9 turns out not to exist, even if the clustering of orbits is explained by some other phenomenon, the effort will not have been wasted. Science is not just about finding answers, it is about asking better questions. There is also a kind of comfort in not knowing everything. A universe where every question has been answered, where every mystery has been solved, would be a smaller, less interesting place. The existence of unknowns, of things that remain hidden despite our best efforts, gives the universe a sense of depth and wonder. It reminds us that we are not the center of things, that our perspective is limited, and that there is always more to learn. Planet 9, real or not, is a reminder of that. It is a question mark at the edge of our cosmic neighborhood, a placeholder for everything we do not yet understand. If Planet 9 is eventually found, it will be a moment of triumph, a validation of the scientific method, and a testament to human ingenuity. It will be proof that even when something is hidden in the darkest reaches of space, invisible to our eyes and eluding our instruments, we can still find it through careful observation and thoughtful analysis. It will be a reminder that the universe, for all its vastness and complexity, is not beyond our ability to comprehend, and it will open new avenues of research, new questions to explore, new mysteries to unravel. What is the planet's composition? How did it form? What is its atmosphere like? Are there moons? How has it influenced the solar system over billions of years? Each answer will lead to more questions, and the process will continue. But if Planet 9 is never found, if the search continues for decades without success, and alternative explanations eventually prove more compelling, that too will be a valuable outcome. It will teach us something about the limits of our methods, about the challenges of studying the outer solar system, and about the importance of remaining open to new ideas. It will remind us that absence of evidence is not the same as evidence of absence, but also that we must be careful not to cling to hypotheses beyond the point where the evidence supports them. Science is as much about knowing when to let go of an idea as it is about pursuing one. In the meantime, we live with the uncertainty. We live with the possibility that somewhere out there, beyond Neptune, beyond the scattered disk, a massive planet is moving slowly through the darkness, tracing an orbit that will take thousands of years to complete. We live with the knowledge that our solar system might be more complex, more dynamic, and more mysterious than we realized. And we live with the understanding that even in the 21st century, with all of our technology and all of our knowledge, there are still profound gaps in what we know. And perhaps that is, as it should be. The universe is not a puzzle to be solved once and for all. It is an ongoing conversation, a dialogue between human curiosity and the natural world. Every discovery raises new questions. Every answer leads to deeper mysteries. And the search for Planet 9, whether it succeeds or fails, is part of that larger conversation. It is a chapter in the story of how we came to understand our place in the cosmos, a story that began thousands of years ago when humans first looked up at the night sky and wondered what those points of light might be, and a story that will continue for as long as there are curious minds willing to ask questions. So as you settle in tonight, as these words carry you toward sleep or toward whatever quiet place you seek, remember that the universe is vast, that the darkness holds mysteries we have not yet solved, and that somewhere out there, perhaps, a hidden planet is waiting to be found. Its existence, whether real or imagined, is a reminder that we do not know everything, that the solar system still has secrets, and that the boundary between the known and the unknown is always shifting, always moving, always inviting us to take one more step into the dark. Sleep well, with the knowledge that even in the silence and the cold of the outer solar system, there are wonders waiting, questions lingering, and mysteries that connect us to something far larger than ourselves. The search continues, patient and persistent, and one day perhaps the darkness will yield its secrets.